Hi, I'm Mark Weitzman. Welcome back to Symmetry and Group Theory in Physics. Today on Lesson 6, I'd like to get into characters and character tables. But before I do that, I want to also review everything that we've done. That's not good. So, what we've done so far is we've covered certain groups. We defined what a group is, the operations, the fact that we have associativity, inverse, and identity. We're talking about finite groups for now. We'll get to infinite groups maybe in a while, but we're talking about finite groups. And there's two kinds of groups. There's many different kinds of groups, but there's especially this distinction between abelian and non-abelian. And abelian is just a fancy word for commutative. So it means that, G1, G2 equals G2, G1. And non-abelian, this doesn't hold for all group elements. And we also discussed some non-abelian group. An example was like permutation groups. Sn for n greater than or equal to 3 is non-abelian. And then the main goal on this thing is that the groups give us symmetry. These are symmetry operators. They act on what we call vectors, functions, basis elements, some vector space, some abstract vector space. And these symmetry operators, the group commutes with the Hamiltonian. So both in classical and quantum mechanics, we can find eigenvectors of both the symmetry group and the Hamiltonian. Now usually it's a lot easier to proceed with the symmetry group, and this gives us a head start. And that's the whole idea of group theory, is when we have molecules or complex molecules or nuclei and everything, if we can use the rotational, the inversion, and permutation symmetries, whatever symmetries we can have, we can find out the nature of the eigenvectors and often get an idea of what the eigenvalues are as well. Usually we'll have to actually solve the problem to get the exact eigenvalues, but we can get the degeneracies and the symmetries from the groups, and that's what group theory is about. Now, the next major thing we talked about was representations. And the important thing about representations is that now we're going to use linear operators or matrices in the case of finite groups to represent the group elements. So we're going to have a bunch of matrices that represents the group elements, and what we're going to show, in order to be a representation, as if you recall, we have to satisfy D is an example of a representation matrix. And we see that this is perfect for the usual multiplication law for matrices. The associativity requirements of group elements just works out perfect for the associativity of matrices. And the non-commutativity for non-abelian groups works out perfectly for matrices also, because as you know, matrices don't commute. So we have these representations, and what we're going to find is that there are several kinds of representations. First of all, there's equivalent. I'll abbreviate representations by reps. So if we can find a non-singular matrix such that S inverse DGS is equal to, let's say, D prime G for all group elements, and this is just, these are like equivalent matrices. It's the same. If this is a representation, if D is a representation, it's obvious D prime is representation. These kinds of representations are called equivalent representations. They're different names for the same things. The matrices look better, but it's just like when you rotate in coordinates and everything. They still represent the same rotation. So inequivalent reps are fundamental, don't satisfy this. We can't find a non-singular matrix S that does this. And those are the reps that we want to find, the inequivalent reps. So whenever I talk about representations from now on, I'm going to pick one representation out of the class of inequivalent reps. I'm not going to always say these representations are inequivalent. It's just assume that two different representations are inequivalent unless I say the opposite. Now the other thing is reducible and irreducible. And here there's a very important distinction. The irreducible representations are like the building blocks. And for a finite group, there's only a small number usually of inequivalent irreducible representations. And all other representations are built out of these representations. And if a representation is reducible, it means the following. It means that the matrices for all G and G can be put in a form where they're what we call block diagonal. There might be like a 1 here, and then there might be like a 2-element representation here, and then let's say a 3-element representation. So this would be 3, 5, 6. This would be like a 6 by 6 matrix, and we can put it in block diagonal form. Whenever we can put something in block diagonal form, it's reducible, and we call this the direct sum. So dg here would be equal to a one-dimensional representation. I'll just call it d1 plus a two-dimensional representation, d2, plus a three-dimensional representation. And the assumption is that each of these ones is also irreducible. If I could reduce this, then I would just have, all ones on the diagonal. And if I could reduce this into a 2 and a 1, I would. So I'm assuming this has been completely reduced. And this is what we call the direct sum. An irreducible representation can't be reduced. It means that we can't get it in block diagonal form. It's just going to have elements. Some group elements are going to have elements at like every position. Maybe some zeros here and there, but different group elements will have different positions. You won't be able to diagonalize the matrix. So one of our goals in group theory with finite groups is we first want to find out what's the symmetry group. Then we want to get an idea of how can we represent that symmetry group. And then we want to reduce it to the irreducible components. For those of you, if you're an undergrad and physics major, you've probably seen things like quadrupole tensors. We've had 3x3 tensors, you know that you can represent it as a symmetric tensor. Let's say this is a tensor T. We can represent this as being the trace of the tensor plus a symmetric tensor plus an anti-symmetric tensor. And this is equivalent to a vector, actually. And the point is that we can get the symmetries in T. This is the trace is a scalar. This is a symmetric, traceless tensor. And this is a vector. So you may have seen these kind of reductions before. With group theory, we're going to do the same thing, but in a much more general way. Because our groups are different. We're not just doing the rotation group. We might have a permutation group, or we might have other types of symmetries. But basically, each one of these irreducible representation represents a different symmetry. They're all part of the original group, but they have different kind of symmetries that stay together. And by stay together, I mean when they act on the vectors, functions, or the basis elements, we can separate these into what we call, one book calls them partners. I'm not sure the exact terminology, but we can separate in the same way we separate the tensor into a trace and a symmetric and a vector. We can separate the components of this 6-component vector into one component that transforms under the one-dimensional representation. 2 components transform under this representation, and 3 components transform under this representation. Okay, now, one of the problems with group theory is you have to have the right balance between, well, there's 2 problems with learning group theory, in my opinion. One is there's a lot of symbols in the notation, and in the next lecture, when I begin to talk about some theorems, I'm going to define like 8 different letters, number of elements in the group, the number of elements in the class, the number of classes, and so on and so forth. So the notation is a little bit, gets cumbersome. There's no way to avoid it. The second problem with group theory is teaching it or learning it. There's a balance that you have to have between complete abstractness, which is sort of like what I did here, and then a practical example. Often the examples are like unwieldy, and it's not easy to find a good example. There's a certain example which I'm going to give, which almost all books give, which is the equilateral triangle, the symmetries of an equilateral triangle, which works out to be the permutation group S3. So I'm going to go through that right now, and we've worked this out already, but I just want to summarize it, and then introduce characters and character tables. Okay. Before I get to characters and character tables, there's one thing I left out which is very important. Just classes. Z has a quote in his book, character is a function of class. So it's a true English. It's a true statement in verbally, but it's also a true statement mathematically. So if we have a group G, and I'm going to start being less abstract. Right now I'm going to do the symmetries of an equilateral triangle. I'm going to label this vertex 1, vertex 2, vertex 3. There are 6 symmetries here. There's what we call the identity symmetry, where we do nothing. There's a rotation by 120 degrees. There's a rotation, and I'm deviating a little bit from my usual notation. I'm going to be doing the rotations as clockwise here. It's rotation by 243 degrees. And then there's a reflection about the 1 axis. And this will be like the 1 axis. And this will be like the 2 axis. And this will be like the 3 axis. So there's R1, R2, and R3. So geometrically, one thing about groups is you can represent the elements in different ways. Right now I'm thinking of this as a geometric sort of relationship. I'm thinking actually rotate the triangle about its center from 1 to 2, 2 to 3, and 3 to 1. So in terms of permutations, this is the identity element, does nothing. This one is the permutation. 1 goes to 2, 2 goes to 3, and 3 goes to 1. This one is the permutation. 1 goes to 3, 3 goes to 2, and 2 goes to 1. This one is the transposition. It's also a permutation. 2, 3, 1, 3, and nope, and 1, 2. So if I were to describe this group as a geometric transformation group, I would think of it this way. If I would describe it as a permutation group S3, and it has 3 factorial or 6 elements. So these are the elements of our group. Now, it turns out there are 3 classes. The identity element always forms a class by itself. The rotations form a class, and the reflections form a class. Now let's give the definition of a class. I'll use this notation, which is sometimes commonly used. If I want to know the class of an element H1, where H1 is in the group, I think of all elements in the group such that there exists a G and H is equal to G H1 G inverse. So this is a set. So if you were to take these elements, the reason why the identity element is always in a class by itself is if H1 is the identity, GG, and this is the identity, and GI, G inverse is equal to the identity. So H is always the identity. So that explains that. But if you were to take like this element, 1, 2, 3, you would look at all elements. Like you could take 2, 3, and then 2, 3 inverse, which is the same as 2, 3. And you can do this multiplication. And you'll find out 1 goes to 2, 2 goes to 3, 3 goes to 2, 2 goes to 3, 3 goes to 2, and 2 goes to 3, 3 goes to 1, and it does nothing on 1. So 1, 2, 3, this element under R1 goes to this element. If you were to do R2, you'd find the same thing, and R3, you'd find the same thing. And if you did an element in the group, you would also see that it stays within the class. So a class is a division of the group elements into disjoint subsets of the original group, such that each element is just a different name. You can see from permutations, this is a 3-cycle, and we talked about cycles and permutations. I'll talk some more when we discuss the symmetric group. And this is a 2-cycle. So all 2 cycles are essentially the same. The identity is just like a 1 cycle. You know, 1. We don't usually write 1 cycles, but this is the identity. So it turns out in the permutation groups, every cycle is just a partition. Like for S3, if you think of all partitions of the number 3, you can write 3 equals 1 plus 1 plus 1. That's the identity with positive integers. 3 equals 1 plus 2, or negative integers. Then you can have 3 equals 0 plus 3. So these 3 partitions give us the cycle structure. Here we have a cycle of 3. Here we have 3 1 cycles. Here we have a 2 cycle, and we don't show the 1 cycle. So that's how the classes are constructed for permutations. They're just cycles. And I'm going to give you a couple of facts, but one fact for classes which is important is the number of irreducible, and I covered this before, I think, the number of irreducible representations of a group is equal to the number of classes in the group. So for this symmetry group, S3, we have 3 classes. That tells us there's going to be 3 irreducible representations of the symmetry group S3. Now, I'm going to put up a bunch of representations of S3. I'm going to have E, so these are the classes. This is the group S3. And I'm going to start giving you representations. First one I'm called D1. Every group has one simple representation. If I represent every element by the number 1, it will clearly satisfy DG1G2 equal DG1GG2. So this is the first representation. It's a one-dimensional representation. We just assign 1 to every group element. Now, it turns out there's another one-dimensional representation. And I'll just write it down, and I'll explain it. And the one thing I want to say is, these 2 representations are the only one-dimensional representations not only of S3, but also of Sn. If we take the symmetry group on any number of objects, there's always 2 one-dimensional representations. The first one is the trivial representation, where we assign every element 1. And the second one-dimensional representation, we assign 1 to every element that's an even permutation. Even. And these are odd. And we assign -1 to the odd permutations. And if you remember, an even permutation can be written as a product of an even number of transpositions. An odd permutation can be written as a product of an odd number of permutations. So clearly, R1 and R2 and R3 are written as a product of 1 permutation. They're odd. But even the 1, 2, 3, this is equal to 1, 2, 2, 3. You can work it out and check it. So it's a product of 2 permutations. So this is an even permutation. So this is the second representation, and I said there's 3 irreducible representations of S3. So I'm going to put the third irreducible representation. Turns out to be a 2-dimensional representation. And I'm just going to write it down and explain it. I think we did this before, but I said we're going to review a lot this lecture. Some of the numbers have changed and everything because I'm using slightly different conventions, but none of that matters. None of that matters till we start doing actual calculations and solving problems. And this 2-dimensional representation, which is irreducible, is simply if we were to assign x and y coordinates to these vertices, x and y, and let's say we call this the origin. And so our first, like the identity does nothing. The x coordinate doesn't change, the y coordinate doesn't change. The other one is a rotation by 2 pi over 3, or 120-degree rotation. And if you remember when we do rotations in physics in 2 dimensions, cosine theta, always a question of where you put the minus sign. Well, let's see if I did it right. Here I have theta equal 2 pi over 3 is 120 degrees, right? So cosine theta is minus 1/2, and you can see for all of both of these, okay. And then sine theta is plus the square root of 3 over 2. So I'm going to put plus here and minus here. So this thing corresponds to that. When we do 240 degrees, it corresponds to that. So that takes care of the 2 rotations. And then when we do a reflection, like I said, if you reflect around the 1 axis, you can see you're going to change the sign of the x coordinate and leave the y coordinate unchanged. That's why. And you can show, if you do a little geometry, that these 2 represent reflections around the 2 and the 3 axis. So that's where this 2-dimensional representation comes from. And these are the 3 2-dimensional representations. Now, we can have higher dimensional representations, and I want to show you where these come from and write down the characters for them. Or I'm going to write down the representations first and then the characters. So since I have it written down, I'm going to erase this. So once again, I'm going to have E, the group elements. E are 2 pi over 3, are 4 pi over 3, R1, R2, and R3. This is the group S3. And so I'm sort of continuing down there. Now I'm going to do the defining representation. I'll call it D3. Here we're going to have 3-dimensional matrices. As always, the identity gets the identity matrix. But now, I'm going to keep that triangle here. 1, 2, 3. So now I'm going to have 0, 0, 1, 1, 0, 0, 0, 1, 0. And as I mentioned one time, we can actually use like 3 basis vectors, like 1, 0, 0. This represents the point 1. 0, 1, 0 represents the point 2. And 0, 0, 1 represents the point 3. 3 objects or points. And you can see that when we rotate, 1 goes to 2, 2 goes to 3, 3 goes to 1. So that's the same thing. 1 goes to 2, 2 goes to 3, and 3 goes to 1. We do our 4 pi over 3 goes this way. And when we do the reflections, what happens with reflection is like 1 basis element, 1 is not changed by reflection. So this is the defining representation for any permutation group. We just rearrange the objects where they go. And the interesting thing is when you look at it, you think this is an irreducible representation, but it's not. It's reducible. And it's equal to d1 plus d2. And I'll show an easy way to see that in a little while. Let's say if you thought it was d1 prime. But so this is a reducible representation. And then there's a 6-dimensional representation. There are 4-dimensional representations also, but I'm not going to go through them. This is called a regular representation, which I discussed one time, where this is the identity matrix for E, but I'm just going to only do one of these things. Here what we do is we label the rows by the group elements, like E, 1, 2, 3, 1, 3, 2. I forgot what I labeled R2. R2 is 2, 3. R1 is 2, 3. R3 is 1, 3, and then this is 1, 2. So these are the group elements. We label them the same way on top, and basically it's just a multiplication table for the group. We put a 1 whenever E times that, whenever G3 equals G1, G2, we put a, wherever that element occurs, we put a 1 there. Otherwise, we put a 0. So I'll just do one of these, and you can check it. For instance, for the R2 pi over 3, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0. There's always a 1 in each row and in each column. But this is different than the defining representation. For one thing, you can see the dimensions are different. And you might think, why do we even bother with the regular representation? It turns out it's useful for theory. But what we'll see is that the regular representation for any finite group, it's going to equal to, it's equivalent to, all the irreducible representations on the diagonal. Like, I'll do this in the case of D6. We're going to have D1 on the diagonal. We're going to have D1 prime on the diagonal. And the number of times that a representation is on the diagonal is just the dimension of the representation. So we have 2 one-dimensional representations, so these are there. And then we're going to have D2 and D2. And the number of times that the two-dimensional representation occurs is just equal to 2. And if we were to have a more complicated group where there were more irreducible representations, like if there was a four-dimensional representation, it would occur along the diagonal 4 times. And this is useful to check this very important theorem. This is another fact, but the sum of the dimensions of the irreducible representations squared is equal to the order of the group. I'll call this NG. And in this case, we have 6, and it's equal to 1 squared plus 1 squared plus 2 squared. So this is a very convenient way to tell you how many irreducible representations there are. You have to take the squares of all of the dimensions of the irreducible representations. They have to be equal to the number of elements in the group. And you can prove this from that representation. So I want to start talking about characters. I want to start talking about some new stuff. So, I don't know. Let me erase this. Characters. The characters is just a trace of the representation matrix. So, for instance, the character in the S3, and they're usually denoted by a letter called chi D, G. So, for instance, this element, the identity element, would have a character of 3. And it's pretty obvious that the character of the identity element in a group is always equal to the dimension of the representation. This has 0 characters, 1, 1, and 1. And that tells you something right away. When I said before, character is a function of class. Because think of it, if we have an element G is in a certain class, let's call it C1, and we take any other element in that class, let's call it G1, we know that G1 is going to be equal to H inverse GH. Now that means in the representation matrices, DG1 is equal to D H inverse GH. Okay, that's nice. But now let's take the trace. The trace of DG1, I can break this down into DH inverse DG. Okay. So the trace of a matrix, when we have a bunch of products of matrices, it's cyclic. So this is going to be equal to the trace the H1 inverse DG DH, because by representations we have to have that. But the trace is cyclic, so we can move this to the front, and now we get the trace of DH, DH inverse DG, using the cyclic property of the trace. Now we can combine these. This is equal to the identity and falls out. So we just get back to the trace of G1. So any two elements in a class have the same trace. So that's the use. That's why characters are so useful. And I'm going to write out what the character tables are. Representations are nice when you have them, but they're not always easy to get. But the character tables, as we'll see this now and a little bit later next time, using some orthogonality theorems, we can get the character tables. Then we can get the decomposition of the representations in a much easier way. So let me just, I want to now I'm going to have the three classes. This is the identity. This is a transposition. This is a rotation class, a 3-cycle. I'll use and there's 2 3-cycles. There's one identity element, and then I'll use I'll use a transposition. This is just a typical member. There's 3 transpositions. Because it doesn't matter which one of these we choose, that's what we get. So let's do the characters. We know that the characters for the one-dimensional representations are just what was there. 1, 1, 1. So here it's going to be 1, 1, minus 1. Now, for the two-dimensional representation, oops. So I said the identity is always the dimension of the representation. If you go back and look at what our rotation matrices were, you'll see that they have a trace of -1, and the reflections have a trace of 0. So this is the character. This is the character table for S3. Now, notice it's square because, as I said before with a fact, the number of classes is equal to the number of irreducible representations. Now, I can, if I want, take characters of reducible representations, and I will right now. So E with 1 element, 1, 2, 3 with 2 elements, and 1, 2 with 3 elements. By the way, different authors, some authors put the dimensions on top and the classes, on the left. So there's 2 ways to do it, but it's a square table no matter what. So for the 3-dimensional representation, the identity is 3. 1, 2, 3 is 0, and 1, 2 is 1. And if you recall, I said before that D3 is equal to D1 direct sum D2. So you can always check this when you think about if you diagonalize and put it on blocks. If this is the decomposition, the characters will add. So let's see if this adds. If we take D1 and D2, we get 3 for the first one, which is right, 0 for the second one, and 1 for the third one. That's good. Now, if I took DR, which is a 6-dimensional representation, the characters of the regular representation are always easy. They're always the dimension for the identity element and 0 for the other things. And I said that DR6 is equal to D1 plus D1 prime plus D2, so direct sums, plus D2. And you can check. If you add D1, D1 prime, and twice D2, you'll get 6. Then you'll get 1, 2, minus 1 is 0. And you get 1 minus 1, then 2 times 0, and 0. So these are the characters of the higher representations. And what we're going to show next time is there's a simple formula when I'm given the representation, if I know its characters, I don't even have to know the representation. If I know the characters, I'll be able to tell you not only immediately if it's irreducible, and you can always, the sum, this sort of tells you, another thing that you have is the sum of the characters over the elements of the group has to be equal to ng. This is a criterion for irreducible. So if you were to take, for instance, here you get 1 squared. There's 2 elements here, so it's 2 times 1 is 3. And there's 3 elements here, 3 times 1 is 6. So that's irreducible. Do the same thing here. Well, minus 1 squared is the same as 1, so you can see it's the same. If you do it here, you get 4 times 1, which is 4. And then you get 1 times 2, which is 6. 0 equals 6. If you try it with these, you won't get 6. You'll get a multiple of 6, but you won't get 6. For instance, here you'll get 9, and here you'll get 3 times 1 is 12. So that tells you that you're getting, it's not irreducible, it's reducible. Here you'll get 36. So that tells you it's not irreducible. Finally, I want to add one last thing. There's things called the direct representation, which I covered earlier. We can have a representation like the direct product of D2 cross D3. And let's say we wanted to do that for a certain group element, let's say R2 pi over 3. You know what, I want to do it, be easier if I do R3 direct product R2. So this is going to, we're going to take the matrix that represents R2 pi over 3 in the 3-dimensional representation, which is just 0, 0, 1, 1, 0, 0, 0, 1, 0. I'm going to take that direct product of R2 pi over 3 in the 2-dimensional representation, minus 1/2 the square root of 3 over 2, minus the square root of 3 over 2, minus 1/2. And if you remember how we do it, what we do is we just go through the first one and like 0 times this matrix. Then we have 0 times this matrix. Then we have 1 times this matrix. And so on. And the one thing I wanted to emphasize, the last thing that I'll finish in this lecture, is the character for the direct product of, let's say, a representation I with representation J. This is easy to, once you go back to the definitions of direct product, this is just the character of DI times the character of DJ. You just multiply the characters. And some of you may remember this direct product thing, like when we have the rotation groups and we have, let's say, spin and angular momentum, and we might add a spin 1, L equal 1 state. We might take a direct product of that with a spin 1/2, and we'll get something like 3/2 plus 1/2. So this is related to what's called Clebsch-Gordon coefficients, and we'll use this more, but just remember for right now that right now with keeping the group the same, there's another thing called the direct product of groups. We're not doing that. We're doing the direct product of representations. The group is the same, and we're taking the direct product of the matrices that represent the group elements, and we get the characters multiply. So next time I'm going to go over the orthogonality theorems, ways to get the character table without even doing any computations, just by using the orthogonalities, and ways to reduce things like this direct product representation is usually reducible, and it will show us how to reduce it. Like here, it turns out this is a reducible representation of the rotation group. So this will be important. I'll see you next time. Thank you.